way. See, no one told you life was gonna be this way.
Alright, so today we're going to be evaluating limits. So I'm going to draw a graph here of a function, and this function can be represented by the equation x squared minus 4 over x minus 2. So this is the graph of this function. We want to find the value of the function at x equals 2. So if we plug 2 into this function, we're going to get 4 minus 4 over 2 minus 2, which is 0 over 0, which does not exist. Obviously, we can see that the value does exist in this function. So what we're going to do is we're going to take the limit as x approaches 2 of this function. And what we can do here in order to evaluate this limit is we can factor out the top to make it x plus 2 times x minus 2 over x minus 2. These are going to cancel out, and we're going to be left with the limit as x approaches 2 of x plus 2. And what we do to solve a limit is we're going to plug in 2 for all the x's in the equation. So in this case, it's going to be 2 plus 2, which is equal to 4. So by evaluating this limit as x approaches 2 of this function, we can find that as the limit of as x approaches 2, we're going to get a y value of 4. And that is true for this function because this y value right here is 4. So this point is 2, 4. And all right, so let's try another problem. So let's find the function. We have x minus 7 over the square root of x minus 2. We're going to take the limit as x approaches 4 of this function. So we're going to be trying to find what the function value should exist at x equals 4 for this function. So let's take a look at what this function looks like on a graph. So we have a graph here. The function is going to look like this. We have a point here, up, and then we're going to have this is going to go like this. And this is x equals 4. So this is what this function looks like on a graph. And as we can see by the graph, we can find that there is no value that exists at x equals 4. This is called an irremovable discontinuity, in which case the function value does not exist at x equals 4. So this function cannot be evaluated with a limit as x approaches 4. We get an answer, it does not exist. No matter what we do to it, we will not be able to get a discontinuity that's removable because there is no removable discontinuity there. What we can do is we can evaluate the limit from one direction. So we're going to evaluate the limit as x approaches 4 from the right of this function. So that is going to be coming from this direction, and that's indicated by this positive sign here. So the limit as x approaches 4 from the right, if we look at the graph, should be negative infinity. So let's see if we get that result. So what we can do is pause. Okay. So in order to solve a function from the right to the left, what we're going to do is we're going to, instead of inserting 4 into the function, we're going to insert a number very, very close to 4. In this case, since it's from the right, it's going to be a positive number very close to 4. And we're going to look at what the graph does when we input these values. So we're going to input in 4.0001 as an example. So 4.0001 minus 7 is going to be a negative number. We'll say a, just for reference. And then the square root of 4.001 minus 2 is going to equal, this is going to be very close to 2, but slightly larger than 2, and this is going to be 2. So we're going to get a very, very small number that is positive. So we're going to get a small positive, we'll call it b. So we're going to have a negative number with a larger number on top and a very small number on bottom. That means that we're going to be approaching infinity. As this number gets, the bottom gets smaller, the number is going to grow. So we're going to have a very large negative number, which means that the limit as x approaches 4 from the right is going to equal negative infinity. And that's represented here by our graph. All right, let's take a look at a different function with a removable discontinuity. So we're going to take x plus 4 over the square root of x minus 2. We're going to do the limit as x approaches 4. So if we solve this function by plugging in, we're going to get 4 minus 4 over the square root of 4 minus 2, which is going to equal 0 over 0, which does not exist. So therefore, we're going to do something else to try and evaluate this limit. So let's multiply by the conjugate of the denominator. So we're going to multiply by the square root of x plus 2 over the square root of x plus 2. This is obviously equal to 1 over 1, so we're not actually changing the value of the function when we multiply by this. So when we multiply this out, the bottom is just going to become x plus 4, and the top we don't have to evaluate. It's going to be x minus 4 times the square root of x plus 2. And if we look at this, because the top is a product, we can simplify this function by canceling the top and the bottom because there's a common denominator. This should be x minus 4. And so we're going to cancel those out, and we're going to be left with the limit as x approaches 4 of the square root of x plus 2. So if we solve this function, we're going to get the square root of 4 plus 2, which is equal to 2 plus 2, which is equal to 4. So therefore, the limit as x approaches 4 of x minus 4 over the square root of x minus 2 is 4. Let me know when. So today we're going to be talking about derivatives. So a derivative of a function is the slope of the function at a given point. So if we have a function x squared plus 2x plus 3, for example, to take the derivative of that, you would use, because this is a polynomial, we would use the function, if we have x to the n power, which in the case of x squared, or x to the first, or in this case it's x to the 0th, in order to take the derivative of this, you're going to do x to the n minus 1, so you're going to subtract 1 from whatever n is, and then you're going to pull that n out in front and multiply it by whatever the variable is. So in the case of x squared, 2 is the n, so we're going to subtract 1 from that, which is going to give us x, and then we're going to put that 2 out in front, so we're going to have 2x. And then we have 2x, this is to the first, 1 minus 1 is 0, which means it's going to be 1, which means that this function is going to be 1, and then we're going to pull that 1 out in front and have just 2. And then 3 does not have a variable, so the derivative of 3 is just 0. So the derivative of x squared plus 2x plus 3 is 2x plus 2. And this means that at any point given on this graph, when you plug in an x and a y value, if you plug in those same values into here, you will get the slope of that function. So we're going to take the derivative of trig functions now. So if we have the function sine of x, the derivative of sine of x is going to be cosine of x, which means that at any given point across the graph of sine of x, the slope of that point will be equivalent to cosine of that value. The derivative of cosine of x is going to be negative sine of x. And the derivative of tan of x is going to be secant squared of x. Alright, now let's look at the other three trig functions. So we have cosecant of x, and the derivative of that function is going to be negative cosecant cotan. And then if we have secant of x, the derivative of that is going to be secant of x tan of x. And if we have cotan of x, the derivative of that is going to be negative cosecant squared of x. So that is the derivatives of the 6 basic trig functions. Alright, so now we're going to use chain rule to differentiate functions where there's an inner function and an outer function. So what we're going to do is we're going to take the derivative of x squared plus 2 cubed. So with this function, you have to take the derivative of the outside of the function first before you can take the derivative of the inside, and you multiply those together. So what you're going to do is take the derivative of the outside, just like if there was an x in here instead. So we're going to have 3 times x squared plus 2 squared and then we're going to multiply that by the derivative of the inside, which is just 2x. So the answer to this would be 6x times x squared plus 2 squared. So that's using chain rule to find the derivative of polynomials when they're in that form. So now we're going to use chain rule to differentiate trig functions. So if we have sine of 3x, this is a pretty simple problem, and we have to take the derivative of this. We're going to first do the outside function. So the derivative of sine of x is cosine of x, so the derivative of here is going to be cosine of 3x. And then we're going to multiply that by the derivative of the inside function, which is 3x, so the derivative of that is just 3. So the derivative of sine of 3x is going to be 3 cosine of 3x. And that is how you use chain rule to differentiate functions.
So, an integral is either a numerical value equal to the area under the graph of some function for some interval, or a new function, the derivative of which is the original function. So let's begin with right-Riemann sum. Let's say we have the integral of 0 to 12 of x squared with 4 subintervals. Now, first we must find the width of each subinterval. So we are going to do the change of x, which we are going to then take b minus a over n. And if we go from 0 to 12, we would do 12 minus 0 over 4, which equals 3. So now we know the width of each rectangle is 3. Now, when we are evaluating a right-Riemann sum, we will now take that equal subinterval of 3 and times it by our x value. So we would do that plus 3 of our x2 plus 3 and so on for the right endpoints of our function. So for this instance, we know that our right endpoints occur at 3, 6, 9, and 12. So we do 3 times 9 plus 3 times 36 plus 3 times 81 plus 3 times 144, which we would get 810 for our right-Riemann sum of from 0 to 12 of x squared. So we already know from before that our equal width is 3. The only difference for left-Riemann sum is that we're using the left endpoints of our function. So instead of going from 3, 6, 9, and 12, we will now be going from 0, 3, 6 to 9. So we will be doing 3 times our value of 0, which is 0, plus 3 times our value of 3, which is 9, plus 3 times our value of 6, which is 36, plus our final value of 3 times the value of 9, which is 81, which equals 378. So now we'll be calculating the area of a curve. So let's say we have the function, the integral from 0 to 12 of x squared dx. This is our graph on the right, 0 to 12, and we are trying to find the area right here. So to find the area, we must do top minus bottom, which is x squared minus our 0, since there is no other function that we are subtracting by. So first we must take the antiderivative of x squared, which is 1/3 x cubed. Now we must plug in our 0 and 12, so we have 1/3 12 cubed minus 1/3 times 0 cubed, which is just left with 576. So now we know the integral from 0 to 12 of x squared dx is equal to 576.
Thank you all for coming to my Theorems of Calculus lecture. Big class today. So, the first topic we will be covering under the Theorems of Calculus is the intermediate value theorem. Now, what is the intermediate value theorem, you ask? Well, I have an answer for you. The intermediate value theorem states that in a continuous function over some interval a to b, the function takes on any given value between f of a and f of b at some point within the interval. So, let's look at an example. Let's suppose f is a continuous function on the closed interval from -1 to 4, where f of -1 equals -4 and f of 4 equals 1. Is there a value c on -1 to 4 such that f of c equals -2.5? Since f is continuous and takes on all the values from -1 to 4, the intermediate value theorem states that at some c on -1 to 4, f of c equals -2.5. That is the intermediate value theorem. Next theorem is the mean value theorem. The mean value theorem states that if f of x is continuous on the closed interval a to b and also differentiable on all points on a to b, then there is a point c in that interval where the instantaneous rate of change equals the average rate of change of f of x. Let's take a look at an example. Let f be a twice differentiable function defined on the open interval. As you can see, we have a table of values there. So that there is a value c such that f prime of x equals 3/2 on the interval from 0 to 6. Now, if we take the average rate of change on the interval from 0 to 6, you can see that it is equal to 3/2. So, since f of x is both continuous undifferentiable and differentiable on 0 to 6, and f prime of x equals and the average rate of change equals 3/2, then at some point on the interval, the MVT states that some c on the interval 0 to 6, f prime of c equals 3/2. Next up is the extreme value theorem. The extreme value theorem states that on a continuous function over a closed interval a to b, the EVT guarantees that the function must have a maximum and a minimum on the interval. Let's take a look at an example. Here we have the closed function over the interval -2.5 to 1 of 2x cubed plus 4x squared plus 2. Now, as you can see, there appear to be some obvious maximums and minimums. Now, if we check that here, you can see at the critical values, there is a maximum, relative maximum here, but what we're really looking for is the extreme values. So there's an extreme maximum here and an extreme minimum there. Now, these are relative maximums and minimums, but that is not what the EVT ensures. The EVT ensures extreme maximums and extreme minimums. Next up is arguably the most important theorem in all of calculus, named the fundamental theorem of calculus. The fundamental theorem of calculus has two main parts. The first part is the antiderivative part, where the integral from a to b of f of x dx equals big F of b minus big F of a, where big F is an antiderivative of f. The second part, equally as important, is the evaluation part, where the derivative with respect to x of the integral from a to x of f of t dt equals f of x. Thank you all for coming to this lecture, and I will see you tomorrow for your final.
Well done, well done.
Thank you.
Today, under applications of derivatives, we're going to be looking at related rates. Now, let's say we have a ladder 13 feet long, leaning against a wall. So here we have a triangle. The ladder is now sliding down the wall at a constant rate of -12 feet per second. We're trying to find the velocity at which the ladder moves to the right when h equals 5 feet. So when this equals 5 at the instant in question, how far away is it moving from the wall? Now, using the Pythagorean theorem, we can find the length of the base, which is equal to 12 feet at the instant in question. Now, we know dh dt. dh dt is the rate at which the ladder moves down the wall, and we have that here at -12. So dh dt equals -12, and that's the rate at which the ladder moves down the wall. Now, we're trying to find db dt, the change of the base the ladder moves away from the wall. So that's what we're looking for with related rates. Now what we're going to use to find this is an equation using the Pythagorean theorem. So let's say we have b squared plus h squared is equal to, let's say, c squared for the length of the ladder. We can change that to L actually, L squared, which is the length of the ladder. So, in order to find the related rates, we need to take the derivative of both sides with respect to their individual properties. So, the first will be 2b dB dt. Now, that's what we're looking for, is dB dt. So, eventually we're going to have to solve for dB dt. I'm going to erase some of this. So, we're going to have 2b dB dt plus 2h dH dt, and we have dH dt, so that's going to be easy to just plug in. Oh, whoops, I put in negative 12 instead of dt, but that's what dH dt is equal to, so that's just something we can plug in, which equals the ladder's length, so L dL dt. And now, since the ladder stays a constant length the entire time and doesn't change, this goes to 0, so we can cross that out, that all goes to 0. We can cancel out these 2's here. So now we just have to plug in for dB dt, b, h, and dH dt, which is what we're looking for. So we'll clear out this top area up here. Give us a little room to work with. So let's say we have our b dB dt. So we know b is equal to 12. So we can plug in 12 for that. We know we're looking for dB dt, which is the rate that the ladder slides away from the wall. So we're going to leave dB dt there. We can solve for it using algebra. And then we also have plus h, which is 5, times dB dt, which we know is equal to negative 12. So this goes to 60, and then 12 dB dt, dB dt, minus 60, because that's a negative. Minus 60 equals 0. So I'm going to erase a little more here. We won't need this anymore. So now we have 12 dB dt is equal to 60 because we added 60 over here to the 0. Divide both sides by 12. And dB dt is equal to 5. So the rate at which the ladder slides away from the wall when the top of the ladder is sliding down the wall is equal to 5.
So now we'll be doing differential equations. Differential equations are an equation involving a derivative. Examples of this could be dy dx equaling tan squared of x plus 5x plus 7. Another example could be dy dt equaling 5t cubed plus 76t squared plus 69. General solutions are find the general solution by finding the antiderivative of the function. The general solution will almost always end in a c or a constant. Example of this is 3x squared plus 5x plus 7. The antiderivative is x cubed plus 1/5 x to the 5th plus 1/7 x to the 7th plus c. Possible general solution could be x cubed plus 1/5 x to the 5th plus 1/7 x to the 7th plus 5. Slope fields, we can display these general solutions by utilizing a slope field, which is able to show all possible solutions to a differential equation. Here is a slope field for dy dx equaling x squared. Particular solutions. We can find the particular solution to an equation when an initial value is given. The initial condition is substituted into the general solution of the function in order to solve for c and find the particular solution.
Alright, so here's an example of a particular solution. So we're going to find the particular solution to the equation dy dx equals 5x squared plus 2x plus 7, whose graph passes through the point 1, 0. So the first step that we're going to do in order to solve this is we're going to anti-differentiate in order to find what y equals. So when we anti-differentiate, we're going to move dy dx over to the right side, and then we're going to take the integral of both sides. So we're going to end up with y equals 5/3 x cubed plus x squared plus 7x plus c. This is the general solution for this equation. So now we're going to find the particular solution by plugging in x equals 1 and y equals 0 and solving for c. So we have 0 equals 5/3 times 1 cubed plus 1 squared plus 7 times 1 plus c, which is equal to 0 equaling 5/3 plus 7 plus c, or negative 26 over 7 equal to c. So now we plug this back into our original general solution for c, and we know that our particular solution for this equation passing through the point 1, 0 is y equals 5/3 x cubed plus x squared plus 7x minus 26 over 7. So now let's talk about anti-differentiation using substitution. So as a review, let's first evaluate an indefinite integral. So we're going to evaluate the integral of x squared plus sine of x dx. This is done by taking the antiderivative of both parts of this function. So the antiderivative of x squared is 1/3 x cubed, and the antiderivative of sine of x is cosine of x. And we're going to have plus c on the end because this is an indefinite integral with no initial condition. So you can check this solution by taking the derivative, and when you take the derivative, you should end up with the original equation. And if we take the derivative of 1/3 x cubed plus cosine of x plus c, we do in fact get x squared plus sine of x. Well, we're now going to use substitution in order to evaluate more complex indefinite integrals. So let's evaluate this indefinite integral using u substitution. So this is going to be the integral of 2x plus 2 times e to the x squared plus 2x plus 3 dx. First, we have to find what u is equal to. So let's use u equaling x squared plus 2x plus 3. When we're solving for u substitution, we always want to use the most inside function for u. So in this case, the inside function is the exponent of e, which is x squared plus 2x plus 3. We can also recognize a pattern here, because u equaling x squared plus 2x plus 3, the derivative of this is going to be something that will cancel out 2x plus 2. So let's take the derivative of u, and we're going to find du dx equaling 2x plus 2. So now we're going to solve to get dx on its own, and we're going to get 1 over 2x plus 2 times du. So now we're going to substitute in dx into our original equation, and substitute u into our original equation as well. So we're going to end up with 2x plus 2 times e to the u times 1 over 2x plus 2 du. So now we're going to simplify this down because we have 2x plus 2 and 1 over 2x plus 2. We're going to simplify this to e to the u du, which when you evaluate the integral of e to the u, you get e to the u plus c. So the last thing that we're going to do is going to reinsert u into the original function. So u is equal to x squared plus 2x plus 3. So we know that our solution is e to the x squared plus 2x plus 3 plus c.
So today we are learning L'Hopital's rule. Let's say we have a function limit as x approaches 0 of sine of x over x. Now if we plug in 0 for the top and bottom, we have sine of 0 over 0, which is 0 over 0. Now there's another way we can do this and find the limit of x approaches 0 of sine of x over x, and that is using L'Hopital's rule. Now L'Hopital rule is if we have a function that is 0 over 0 or infinity over infinity, we can take the derivative of the top. So if we take the derivative top of sine of x, we get cosine of x, and we take the derivative of the bottom, we get 1. Now we have a new function, which we can now do limit as x approaches 0 of cosine of x over 1. Now, if we plug in 0 for x, we have cosine of 0 over 1, which equals 1 over 1, which equals 1. Which therefore, we now know that the limit of x approaches 0 of sine of x over x really equals 1.
Alright, let's try our harder problem. So we have the limit as x approaches 0 of cosine of x minus 1 over e to the x minus 1. And if we try to do this limit, we get cosine of 0, which is 1, minus 1 equals 0. We have e to the 0, which is 1, minus 0 minus 1 is 1 minus 1, which is also 0. So we have an indeterminate form. So we're going to take L'Hopital's rule, and we're going to get the limit as x approaches 0. We're going to take the derivative of the top, we're going to get negative sine of x. And we're going to take the derivative of the bottom, we're going to get e to the x minus 1. And if we plug in 0 here, we get negative sine of 0, which is going to equal 0. And we're going to have e to the 0, which is 1, minus 1, which is also 0. So this is another indeterminate form. So we're going to repeat once more. So we're going to take L'Hopital's rule again, the limit as x approaches 0, and the derivative of this is going to be negative cosine of x over e to the x. And if we take the limit as x approaches 0 of this, we're going to get negative 1 over 1, which is equal to negative 1. So the limit as x approaches 0 of cosine of x minus 1 over e to the x minus 1. Using the L'Hopital's rule, we were able to find that it's equal to negative 1.
9, 8, 8.
Man, stop backseat
2.
playing. Stop it! Alright.
That one I'll go. Draw.
Okay, we're good.
Draw. Draw.
What the heck, man? There we go.
Draw. You suck at this game.
Apparently.
Tesla? What the heck? Excuse me, what are you guys doing?
Playing racing games, duh.
Hey, sir.
Out at you from the hiding place, like acid and oil on a madman's face, as reasons tend to fly away, like lesser birds on the four winds, yeah, like silver scrapes in May. And now the sand's become a crust, and most of you have gone away. Yeah.
Sure, you may have the Lego set Death Star, but can you chug a sparkling water and not burp? Gross. Oh my gosh! What do I do?